replacement of silicon dioxide with another gate dielectric is needed. So the MOS structure itself is a capacitor. So to understand the physics of the MOS capacitor on the theory of capacitance. So what we have here, we can see that the capacitance depends only on the geometrical factors such as the plate area and the plate separation, which is in our case now here, the D here is the thickness of the oxide or the dielectric. So in order to increase the capacitance value, normally the thickness of dielectric should be reduced. However, in the case of silicon dioxide, reduced thickness results in carrier leakage as the breakdown strength of the silicon dioxide cannot bear the thickness below than 1 nanometer. So if the thickness is reduced below than that, the carrier leakage will occur due to electron quantum tunneling. And of course, it will result in catastrophic destruction of the device. But not only that, it becomes more difficult, of course, at a very minute size to produce. And of course, it will be very hard for us to measure accurately the films of such small thickness. Hence, the reliability of silicon dioxide films against electrical breakdown decline in thin films. Therefore, for this reason, but principally due to leakage, it is imperative for us to replace the silicon dioxide with the high K dielectrics to reduce the direct tunneling gate leakage current. So silicon dioxide dielectric of K value of 3.9. So the dielectrics featuring K higher than 3.9 are referred to as high K dielectrics. A higher K value means a greater capacitance at greater thickness. So with greater capacitance, we can have faster transistor, and thicker dielectric will reduce dielectric leakage, hence for cooler device, and a long way to go for further scaling. So guys, here is the starting point of my work. So remember the little bit of good thing. So the little bit of good thing that I've done here is that I go and search for an alternative metal oxide to replace the silicon dioxide in the MOS system, so that further scaling of semiconductor devices are possible. So alternative metal oxides such as hafnium oxide have been used, but it is not without problems. Even though it has a very high K value of 25, its band gap value is only 5.1 eV, which is considered low for future advancement. And moreover, hafnium is a rare metal, and of course, it is very, very expensive. So a better material such as aluminum oxide is needed to be used as gate oxide. So aluminum oxide has the advantage of being thermodynamically stable materials. It has a band gap of around 8.8 eV and relatively high K value of 9, but yeah, 9 is not good enough. So that's why we engineered these materials to improve the K value of aluminum oxide. How are we going to do this? So we doped aluminum oxide with hafnium. So in this work, a substitutional doping, a doping whereby some metal atoms are replaced by other metal atoms at a particular site in the crystal lattice, so that we could have a normal hafnium. So this is a very important strategy so as not to change the crystal structure of the material, which may change its properties. So what is the method that I use for this substitutional doping? So I had found a special synthesis method, which is self-propagating combustion method, okay, well known as the SPC method. So it is known for its simplicity, it is inexpensive, but most importantly, it can yield high highly pure materials in relatively large amounts. Okay, so to come up with a novel aluminium hafnium oxide, so I use the aluminium nitrate nonahydrate, the hafnium tetrachloride, and citric acid monohydrate as the starting materials. So after careful calculation of the starting materials, all of them were dissolved in ultra-pure deionized water using the magnetic stirrers until a clear solution was formed. Then the solution was heated on a hot plate at 350 degrees C until combustion occurred and precursor materials were obtained. So I found that the combustion process started with the bubbling of the solution. And then the solution turns light yellowish in color, which indicate the citric acid is converted to methyl malate anhydride. But just before the combustion, the solution was thickened and smolders, releasing thick yellow fumes of nitric acid during the complexation reaction. And finally, it produces a white yellowish powder precursor. So from here, I could know that the SPC method using citric acid as a combustion agent is observed to be a less violent reaction compared to other combustion agents such as urea and glycine. And this is the winning point, because if the combustion produces a very violent reaction, so this will be detrimental to the production of the precursor itself, because the fine powders will be thrown everywhere in the fume cupboard and very little will be left in the beaker. So then the precursor were grounded using the mortar and pestles and to produce very fine powders. So, and I brought the powders. Then the powders were characterized by the simultaneous thermogravimetric analyzer, the STA, and for me to get the thermal profile, where from there I could get the right annealing temperature to get pure aluminium hafnium oxide. So here we go. Okay, these are the results for the STA. So this is the thermal profiles of the aluminium oxide. Okay, for aluminium oxide, there are generally two wake losses in the TG profile, which are marked as region 1 and 2. So the first wake loss in region 1 have a wake loss around 7%, okay, at the temperature range of 30 to 180 degrees C, accompanied by an endothermic peak that is attributed to the loss of water that are still remaining in the precursor. So for that, the precursor is proposed to be anhydrous aluminium citrate here, okay, as given in the equations. And the proposed chemical reaction shown in this equation indicates a weight loss of 6.8%, which is very close to the experimental value. So in second region, a major weight loss, okay, occurring at the temperature range of 180 to 600 degrees C, accompanied by a broad endothermic peak, then followed by exothermic peak that are attributed to the decomposition of the precursor and formation of pure aluminium oxide. So the weight loss for the decomposition of aluminium citrate here, okay, into the aluminium oxide is calculated as shown in the equation here and found to be 71.5%, which is very close to the experimental value of around 65% here. So as we move further, we can see that there is a small exothermic peak appearing at around 900 degrees C without any weight loss. There is no weight loss here. Okay, so it is basically assigned to a phase transformation from a delta aluminium oxide into the theta aluminium oxide. Okay, so the second small exothermic peak occurring at around 1150 degrees C is attributed to the transformation of theta aluminum oxide to the most stable phase, alpha aluminum oxide, which is the most stable phase of the aluminum oxide materials. Okay, so this is the thermal profile for aluminum hafnium oxide. We can see here there is slightly different in terms of region of weight loss, where they have three distinct regions of weight losses, and this had brought to three proposed chemical reaction, where all of them show very good agreement with the experimental value. So the phase transformation from delta, theta to alpha can also be observed from the aluminum hafnium oxide precursor. And it shows that with the hafnium in the compound, the decomposition temperature range increases from around 200 to 620 degrees C. And for that, it can be said that the substitution of hafnium in aluminum oxide that increases the temperature of the phase formation of highly stable alpha aluminum oxide. So since a pure phase is formed at about 1150 degrees C, so I choose the annealing temperature of around 1300 degrees C for 48 hours in order to obtain high purity alpha phase materials. After the annealing process at 1300 degrees C for 48 hours, as shown here in the figure, are the aluminum hafnium oxide materials at the respective stoichiometry of X to 0.001, 0.002, and 0.003. So all of these materials had undergone the X-ray, diffraction, the XRD, field emission scanning, electron microscopy, PSEM, the energy dispersive X-ray analysis, the EDX, and finally the ultraviolet visible spectroscopy, the UV-vis. So did I get the alpha phase materials? Okay, so the XRD analysis will tell us whether I got it or not. Okay, so here in the figure are the XRD patterns of the aluminum oxide and novel aluminum hafnium oxide materials. So it shows that all the peaks are indexed to the hexagonal crystal structure of aluminum oxide, so which is the alpha aluminum oxide with a space group of R3C as confirmed by the reference pattern of the ICDD. So the diffraction patterns show that the aluminum oxide and aluminum hafnium oxide materials are single phase, indicating that the hafnium ions are successfully substituted into the aluminum oxide structure. So where we can say that they are all pure and no impurities are present in the sample. So that goes for the structural analysis. And now let us see the morphology of the materials and their crystallite size. So these are all the images of the aluminum oxide, aluminum hafnium oxide at 0.001 up until 0.003. So the pure alpha aluminum oxide powder, we can see here, consists of large chunks of particles where there is tiny spherical crystallites embedded in it. So the morphology is quite similar for the hafnium doped samples, the novel aluminum hafnium oxide samples, but the small spherical crystallites embedded in chunks are larger as the hafnium content increases. So the crystallite size range from 400 nanometer to 1000 nanometer. And move further to determine the elemental composition of a stoichiometry of a sample. So the energy dispersive X-ray analysis, or EDX, is the proper technique to be used. So the EDX detector is basically integrated with the SEM. And the elemental composition of the materials are determined by measuring the energies of the X-ray emitted from the area being excited by the electron beam. so that the compositional information can be acquired by the EDX. So this analysis had helped me in order to confirm the presence of hafnium ions in aluminium oxide. So what we have here is aluminium and hafnium elements are clearly identified in the corresponding spectrum. So we can see that aluminium is detected at the K alpha of around 1.4 keV, while hafnium is detected at M alpha 1.6 keV and L alpha at around 7.9 keV. So the EDX results have substantiated and supported the results from the XRD. So therefore, both XRD and EDX results, it can be concluded that hafnium has been doped in aluminium oxide, and this is a direct proof that the substitutional doping is successful. So all the SDA, the XRD, FESM, and EDX had provided us information about the material properties. But so next, I'm going to bring you all to look on the materials functional properties. So the functional property that had been analyzed for these materials is gap energy. So, the band gap energy values of all materials were studied using the UV visible spectroscopy. So in this figure, these are all the absorption ages of all materials in the wavelength range between 200 to 300 nanometer. And we can see that aluminium oxide and the noble aluminium hafnium oxide materials have two absorption ages. Okay. The hafnium oxide, which exhibit one absorption age. Okay, so here first absorption age is identified as the band gap, and the second absorption age is attributed to transitions due to cation vacancy. So it is observed that there is a shift to the right of the absorption age with the increase of hafnium content. So this implies band gap narrowing of the dope materials with the increase of hafnium content because the band gap energy is actually inversely proportional to the wavelength. So that is first expectation that we could interpret from the absorption age analysis. The band gap energies are obtained by the torque equation. So the first torque plots over here depict the electronic band transition extracted from the first absorption age, while the second one depicts the electronic band transitions is extracted from the second absorption age. So the band gap value of aluminium oxide obtained here is around 6.06 eV. This is actually much smaller than the conventional values of 8.8 eV. So the decreased band gap value is attributed to band gap change of the nanocrystals of aluminium oxide as it can be seen from the tiny crystallites in the previous semi-micrographs. So it is known that the nanocrystals of metal oxide can exhibit band gap change. So band gaps of the aluminium hafnium oxide samples have been found to be lower than aluminium oxide. And these values range from around 5.86 to 5.92 eV. However, all the noble aluminium hafnium oxide materials have band gap values that higher than the hafnium dioxide. So this indicates that the substitutional doping of aluminium oxide with hafnium has the ability to lower the band gap of the doped aluminium oxide compounds. So it is established that nanocrystals exhibit band gaps quite unlike the values of conventional crystals. So crystallite size affects unique cell parameters, which in turn affects the band gaps of the materials. So the more the hafnium content, the lower is the band gap value of the material. So the relationship between the band gap and hafnium content seems to have an exponential function in the form of these equations. Okay, where here Eg is the band gap and the X is the mole fraction of the hafnium. The decrease in band gap of the hafnium-doped materials is attributed to the presence of the dopant hafnium ions in the crystal lattice. So we know that hafnium has a valence of +4 and aluminium has a valence of +3. So therefore, the presence of hafnium in aluminium oxide will introduce extra available electrons. So this will create the donor levels in the energy bands as illustrated in figure A, where we have a comparisons between pure aluminium oxide and oxide, which will narrow the band gap. So this is the donor levels. Okay, so the introduction of hafnium in the lattice of aluminium oxide materials had modified the energy bands of the dope compounds. So this will result in the new hafnium dope materials to be an extrinsic semiconductor. So the band gap values for hafnium doped samples decrease with respect to the aluminium oxide, where the presence of hafnium introduces an extra electrons in the materials, okay, due to the +4 state as hafnium as illustrated in this Lewis structure, okay, for both aluminium oxide and aluminium hafnium oxide. So from my reviews, I found that when I compared to other dope materials such as chromium doped aluminium oxide, titanium doped aluminium oxide, and my novel aluminium hafnium oxide material seems to be more suitable as a candidate for most application because of its higher band gaps. So as to conclude from this work, okay, the novel aluminium hafnium oxide for X equal to 0.001 up to 0.003 materials have been successfully obtained from the SPC method. So the band gap narrowing of the materials are observed with respect to the aluminium oxide material due to the introduction of donor energy levels of the band energy of the materials. But however, the novel aluminium hafnium oxide materials have a higher band gap than pure hafnium oxide. Okay, so very well. All of these works had been published in two journals, which is the journals of chemistry, of materials chemistry and physics, and the other one is results in materials. So for that, I want to express my special thanks from my heart to my mentor, my dear Professor Dr. Nolida Kamaruzaman, who is a very professional, a very thoughtful person, and a very kind-hearted person. And to Professor Dr. Si Zhu Zhao from Liverpool Jiaotong University, and Dr. Muhammad Firdaus Omar from University Technology Malaysia. They were both my co-supervisor during my PhD. And not to forget, I would like to express my gratitude to Professor Dr. Rihanum Yahya Suband, who is my head of center in Institute of Science, and to Professor Insignio Dr. Muhammad Rusoh Mahmud, who is currently my head of center for Center for Functional Materials and Nanotechnology. Thank you to Professor Dr. Zurina Shamari, the Director of Institute of Science, And of course, Professor Dr. Farida Zuraina Muhammad Yusof, the Dean of Faculty of Light Sciences, and not to forget Associate Professor Dr. Zuraida Husaimi, the Timbalan Pengarah of Institute of Science. And of course, my special thanks also to my good friends, Dr. Muhammad Sufri Mastuli, and my co-researchers, Dr. Muhammad Firdaus Kasim, Associate Professor Dr. Tanwini, Dr. Nur Aimi, Dr. Nurhana Badar, Dr. Muhammad Lokman Ibrahim, Puan Kalima Elong, and Cik Nur Fadilah Chayet, for so many of them. And of course, special thanks to Puan Nur Ashikin Kamarudin, the Senior Science Officer of CFMN, and Puan Hasdiana Hashim, Encik Muhammad Zaidi Malan, and of course, Encik Muhammad Fikri Ramli. Okay, so if you have any inquiries or interest in collaboration, so please do contact me via my email or text me. So if anyone out there looking for any opportunity in postgrad study, so please do not hesitate to contact me. So for that, I would say thank you very much for this opportunity. And may I return it back to you, Dr. Sufri.
Okay, thank you very much, Dr. Annie. It's a very full of information, a lot of graphics and facts. From the chats, because we still have times, you are very good managing your times. You just deliver in 30 minutes. So it's meant that you're open for a lot of questions, I believe. A lot of, most of the audience here are eager to ask questions, I think, but they are very shy. So from the chat room, I have one question. I try to read out. Dr. Annie, what is the reason for the substitution of, I think, substitution aluminium side with hafnium in your compound? What is the reason? Why you substitute your aluminium with hafnium? What is the main reason?
Okay. So
Why hafnium? Why not other elements in the aluminium side?
Okay. So one by one, you tak shoot some more questions. So one by one, I answer the question. Okay. So to the person who asked me this question. So basically, why I choose hafnium, not the other types of element, because hafnium oxide itself is already implemented in the processor for Intel. Okay, but Intel have the problems with the price. With the price of the price of the hafnium, but hafnium performs very well with the Intel. If you found the i5, i7 processor, they use the hafnium dioxide as the dielectric, as the insulator in the most structure. So hafnium has been it has been used in commercial. So because of its price and because of its its properties as a rare metal earth, so that's why it is my interest to choose hafnium, okay, to put some of it into the aluminium oxide. So why aluminium oxide? Because it is abundant, okay, and of course because of its thermally stable, okay, because for the semiconductor fabrication process, we must have a very stable oxide materials that can confront up to 1000 degrees C of process fabrication. So that's why I choose the aluminiums over the aluminium oxide, and I choose the hafnium.
Oh, okay. We still have another question. What is the key value for your alumina, for your compound?
Okay. So
what is the key value? Because you mentioned just now, a key is 25 is better compared to K9. So what is your compound? What is the K value?
Okay, so of course I didn't mention the
From
K.
from Dr. Misbah, I think. It's my
Yes.
neighbor.
Oh yes. All right. So basically, in my presentation, I didn't mention about the K value of my aluminum oxide powder because I measured the dielectric value, the K value, in the form of thin films. But kalau in the form of thin films, ET and CPI give me 2 hours time, so then I can proceed with my thin films properties.
Yeah, I think you can book for another webinar series if you wish. I think wakil kat sini ada kot nak dengar. Right.
Okay,
Do you calculate the K value?
back to the K value. So I am expecting. So basically, when I engineered these two materials together, the aluminum oxide and the hafniums. Okay, so when I engineered them together, it is my hope to increase the K value. So it must be higher than the K value of aluminum oxide alone, but it will be lower K value from the hafnium oxide side. Okay, so this is my expectation because so to be honest, basically I got around 20 K value for my materials ni sebenarnya. Okay, so that is this is very important because the K value and the band gap energy has a very close relationship. They are inversely proportional to each other. So when we have aluminium oxide with around 8.8 EV to 9 EV, so that is why its K value is much lower than the hafnium oxide K value, because hafnium oxide has, if you see there, hafnium oxide around 5.1 EV, but with higher K value of 2.5 of 25. So at the end of as you can see my my results, okay. So the final compound of the aluminum hafnium oxide, I managed to get around, go back to it, I managed to get the highest band gap energy that I got is 5.92. So I do expect that the K value of of my novel aluminum hafnium oxide will be increased compared to the host materials of aluminum oxide. And yes, so when I deposit it as a thin film, I managed to get around 20 K value.
Okay, thank you for the question. Dr. Ini, do you mind to entertain a more question? Because I believe your friends from Department of Physics, a lot of curiosity. Okay, Dr. Ini,
Yes.
back to the question of Dr. Misbah just now, is you said you're expecting this minute you did not calculate, isn't it?
Yes.
Okay, what is the instruments to measure the K value?
Okay.
The instrument that you will use.
Okay, so I didn't use I didn't do a direct measurement with my powder samples. So after I obtained this aluminum hafnium oxide, the novel aluminum oxide, I used the sample for me to deposit thin films on the silicon substrate. So when I obtained this layer of oxide on the silicon substrate, I used the CV measurement. Okay,
Oh, okay, right.
to obtain the dielectric value. This is when I do the CV measurements, the capacitance voltage.
But then Annie, what is CV? Because I'm chemist and not physics. What is CV? Is
Yes,
it curriculum vitae?
yes. For semiconductor, it is a
What is CV?
voltage
Oh, current voltage.
versus voltage, not current.
Okay, okay. Continue.
All right. So from there, from the accumulated value of capacitance, I will directly calculate the dielectric value for my oxide layer. Okay.
Okay.
By using a simple equation as I
I hope Dr. Misbah is still here. He's very interested with the key value. I try to open the open the discussion. Okay.
Yes, any more questions?
Okay, another two. I think
Yes,
you know very well Dr. Farah.
yes,
Farah here is from your department as well. She
thank
asking about how much the leakage current from the device can be affected by this novel material.
Okay, so,
Okay.
surprisingly, okay, so when that actually is a advanced question basically.
Yeah, I think that the Farah always give a tough question. It's not only for her students, but also
Oh,
for the speaker, I think. Leakage current. What is your comment regarding her questions?
right, no problem. Okay, so what I got for the dielectric for the leakage current for this novel materials, so I managed to deposit down below to 5 nanometer thickness of oxide layer. Okay, and for that I managed to reduce to reduce the leakage current density of the novel material. So it's around -6 to -5 leakage density. So it's improved, and what else? So the leakage current density can be reduced because my novel material, the aluminum hafnium oxide, basically it has a higher K value. So with higher K value, it has higher capacitance. And of course, with higher capacitance, we could have a faster transistor. And of course, it will reduce the leakage current.
Okay, all right. We quite a lot of physics terms here. We have a key value, leakage current. I think the chemist is that blur. Okay, I think we have a representative from a chemist. I think Dr. Nazri Zawati. Her question is instead of study the bin gap slash a photocatalytic study, is it the material suitable to be used in other application? First, you mentioned in the most, I think because you elaborate a lot of bin gaps. So I think that the Nazriza think about photocatalytic application. Do you think your compound can be used in another application instead of MOS? What is?
So the first things that I have looked, of course, yes, semiconductor materials, they have lots of applications to it. All right, but bear in your mind that what I have done here is that if you found that found that in my presentation just now, the aluminum oxide and the aluminum hafnium oxide itself has various phase, such as delta, theta, and of course the most stable phase is the alpha phase. So yes, a different phase will give you different types of applications, such as delta aluminum oxide. It can be provides can serve the optical, the sensor applications. But for alpha aluminum oxide, it is special for the most application because of the very stable phase of alpha aluminum oxide, alpha aluminum hafnium oxide. It can sustain the semiconductor processing of metal oxide semiconductor.
Oh, okay. All right. I think I missed a few questions. Okay, back to the question number one. Still, you remember regarding the substitution of hafnium. Okay, I think because the person is keep pop up the question, I think I missed the points. How do you verify? How do you confirm? Or how do you know the hafnium substituted in aluminum? How to confirm?
How to confirm? Okay, so the
Yeah,
first,
I think that question is how to confirm.
okay, how to confirm? So we can use the X-ray diffraction analysis, or the I have been show you. All right. So the first thing, I use the XRD, of course, to confirm that the hafnium oxide, that the hafnium element have been substituted into the aluminium oxide structure. Because, okay, from the XRD, we can see that all peaks are indexed to the patterns of the host materials. Our host materials here is the aluminium oxide. Okay, so since there is no other peaks that represent the hafnium structure or any other impurities, so we can confirm that the hafnium is successfully substituted into the structure of aluminium oxide.
It's meant that regarding any structural confirmation, it should be done using the XRD, isn't it?
Yes.
Yeah, in the interstitial of substitutions. So XRD is one way to confirm either the phenomenon happen or not happen.
Yes, true.
Okay, correct. Okay, I think, okay, another question, because we still have time, we appreciate the time given by the NCPI. We try to use it up to the maximum. Another question from the audience. Can you please explain the decrease of the bin gap due to hafnium aluminum side for the potential application of the material? You get it, the question? Can you explain the decrease of bin gap due to the substitution for the potential application? I mean, I think her or his question is, what is the significance of study the bin gap reduction? Because the bin gap is reduced upon the substitution. What is the significance of reduce the bin gap for the most application? I know I think I know the answers, but you can explain that one. It's
Okay.
back to the key value, I think, because you keep expecting. So yeah, the answer is there.
Mm-hmm. So yes, when we, of course, when we do research, we do first thing that we make is hypothesis. Okay, so of course, whether or not we complement the hypothesis or what, so it depends on how we're going to strive for it. Betul tak, Dr. Sufrin?
Yeah, correct. Because I understand yours because we're discussing a lot about your research. Okay.
Yes. Okay, so the things here, why is it important for me to decrease to reduce
Bin gap.
the gap? Okay,
Yeah.
so the things here, bear in your mind that now, bear in my mind. Okay,
Yeah.
firstly,
Be in
when
all mind.
to go to use the aluminium oxide, so I recognize aluminium oxide has a band gap of 8.8 eV, around that value. Okay, so but with that value of band gap, it consists of a lower K value. For your information, if you want to replace the existing oxide dielectric, which is the silicon dioxide, okay, and of course to make sure that your oxide is applicable in a very long-term period, so we must at least have at least 12K value. Okay, so that's why when we have another element, when I have another element, which is the hafnium oxide, which have a lower band gap value. So of course, my hypothesis, of course, it will lower when the hafnium element is substituted into the aluminium oxide structure, it will lower down its band gap value, the host material's band gap value. So when the band gap value is reduced, okay, the K value will be increased because it is established, it is physics of law, where the band gap is inversely proportional to the K value. So I think
Yeah, I think it's answer all the question because you're expecting the key value. This why you are very focused on the bit gap analysis because they have inversely proportional between the key value and also the bit gap energy. Is that correct?
Yes, doctor.
Okay, I think Dr. Annie, I think you, the speaker, received a lot of questions from this webinar series. Apologize because I'm the moderator. I'm asked a lot of questions. I think we still have 3 more minutes because the question all from the audience. I have one last question. I think one last question. I have a lot on my paper, but I think just one last. What is the significance to study the to do the substitution instead of interstitial? Yeah. Why
So,
substitute? Why not interstitial?
all right. So, when we say substitutional doping, so when we say doping, okay, doping is when we introduce impurities to our compound, okay, and with the substitutional, we substitute the ions of any impurities towards the host material structure. Okay, so why substitutional over the interstitial? Okay, because I want to sustain the properties of the aluminium oxide, especially its thermodynamically stable properties. So that's why.
Okay, I think you give me a very solid reason, I think. Okay,
Yes.
Dr. Annie, thank you for you again. Thank you very much. And we pray for you many success to come with your research works in the future. Maybe before we close, do you have something to closing or words or what? Say thank you to all right?
All right. I just want to say thank you to all the reviewers, all the viewers, participants, and thank you very much for your kind support, your kind words. And actually, in my FB, in my Instagram, I still receiving lots of praise, a lot of support. Thank you very much for that. Thank you to all my friends. Yeah, of course. Please, if you actually, I am eager for my coming years as a researcher. So to all my students, I hope there are my students in the viewers. So I do open for the postgrad opportunity, and please you can come and have a talk with me. So maybe we could have a bright future together.
Okay. Yeah,
Very
you're
much.
so kind, Dr. Annie. Okay, thank you very much, all the viewers, for your great support and cooperations. Please find the registration link in the chat box for your registration of attendance. We are going to have another or more webinar session in coming days. Keep updated with the CPI Facebook or email. Do stay alert and connected to our webinar messages in email. As we are currently in CMCO in Klang Valley, do stay safe, avoid crowded places, less physical contact, and stay connected online. Kita, jaga SOP. For that, Assalamualaikum warahmatullahi wabarakatuh. Bye-bye.